Okay, intermolecular forces, part 3. Why do things that are not polar and not ionic even form a liquid or a solid anyway? Well, first of all, those forces tend to be weak, but there's a term for that called London dispersion forces. So, nonpolar molecule whacks into other nonpolar molecule, forms things called temporary dipoles, and that's why we can say something like oxygen can be liquefied. Generally, these things are weaker, but there's a huge spectrum of the strength of these forces. So after today, we'll be done with intermolecular forces and we'll move on to their application. So let's talk about the forces between nonpolar molecules right now. Well, hi everybody, hi, Mike here. We're going to polish off the last of intermolecular forces. So we're going to start off with the question. Now look, we have discussed forces which involve ions. We've discussed forces which involve polar compounds. And today we're going to talk about nonpolar compounds. And the question would be, how can they ever become a liquid? They should have no forces whatsoever, really, and that's not true. There are a third kind of force. Well, actually, let's go through. Ionic forces, ion dipole forces, dipole forces, and then hydrogen bonding. And so now, if you've got nonpolar compounds, they have forces between them, or else, of course, they would never liquefy or solidify. And so those forces are called London forces or dispersion forces or London dispersion forces, named after Fritz London, a German person, and Charles Dispersion. Not really, not the dispersion part, I just made that up as a joke. So here we go. What we're going to do is we're going to draw a little diagram. Nonpolar compound comes into contact with other nonpolar compound. And what you've got there is equal distribution of the electron cloud. So there's two ways you can visualize these. So oxygen, O2, comes up to another oxygen, and they whack into each other, kapow. And that deforms the electron cloud, and so you would get, some sort of deformation of the cloud. And of course, where there's more electron cloud, that's going to be the side with a partial negative and then partial positive. Let's say the same thing happens to the other molecule. It's like a big old car wreck, right? And you got dents in this thing. Keep in mind, the electron cloud is fairly loosely held. Remember that an atom, the nucleus is kind of like a pea, and the cloud is like a large stadium. So it's not held very tightly. It's very malleable. And now this will cause what we call a induced dipole. Sometimes they're called instantaneous dipoles. And so that's one way to look at it, the collision theory. The other way to look at it is that just two nonpolar compounds coming into proximity with each other, the electron cloud is not a rigid sort of thing, either physically, it's mushy, but even conceptually. The electron cloud is like a probability density of where the electron is probably going to be. And so sometimes the electrons deviate from that, So it could be like the nucleus is going to say, like, where were you? And most of the time you'd be able to say, but then there's that little part that you went and skipped off to the bar or something. No, that's a terrible example, but sometimes electrons aren't exactly where they're predicted to be. And so there's some sort of modulation in the cloud. So once in a while, the cloud will sort of have a little blip where the electron kind of is more tended to one side than another, and those will cause dispersion forces. And so just being next to another nonpolar compound, there doesn't even need to really be motion. You can have these temporary dipoles that happen, and that's what makes an attraction. So collisions and just being in proximity. So theoretically, every kind of compound has London dispersion forces. Something can be polar, but they also are moving around. They can whack into each other. And so every compound, all compounds have London dispersion forces. So keep that in mind. Everything has London dispersion forces, but if it's a nonpolar compound, then what you got going on is that is the only force. And now, what makes these forces big or small? There's something called polarizability. So the further out, so this determines the strength. If you got a big old nonpolar molecule with a big old mushy cloud, that kind of thing is going to be more polarizable, and the London forces are going to be stronger than something that's kind of compact. Take a look at the halogens. Let's just even go through the halogens. Fluorine, F2, that's smaller because you're dealing with N equals 2 is the furthest out cloud, right? You go down to chlorine, so fluorine's a gas. Chlorine's a gas, it's neighbor to the south of it. Now you get into bromine, bromine's a liquid. You get into iodine, that's a solid. Another really kind of pertinent example would be if you take hydrocarbons. So if we just take carbons and put hydrogens on them, and we will end the course with this. There's a little kind of rule of thumb. It's CnH2n plus 2. So methane, CH4. And then you got ethane, C2H6. Now keep in mind, there's only two kinds of bonds in these compounds. So this would be strength we're going to talk about. There's only two kinds of bonds. There's carbon-carbon bonds. Those aren't polar. Carbon-hydrogen bonds with an electronegativity of carbon being 2.5 and hydrogen being 2.1. There ain't no polar bonds in this whole thing. You ever go to the store and get yourself a new tank of propane? All these things are gases. And you could say, hey, it's swishing around in there. Well, we're going to talk about that next time. That is because it's pressurized. So you can go all the way up to a 3-carbon chain, and those things are gases. Now, we go to one more carbon, butane, which is what's in cigarette lighters. Which probably there are not many of anymore because no one smokes anymore, hardly. There's like 1 square foot in the whole state that you could smoke. That's a liquid. So as soon as you go 4 carbons big, it's polarizable enough to actually become a liquid so that its boiling point would be above room temperature. This goes on a lot. You go pentane, C5H12, octane, right? Sounds familiar. That's in gasoline. As a matter of fact, all this range of liquids, all up to about, I don't know, 20-something carbons, those are all liquids. And the boiling point increases as I go and add carbons. So if you had something like 12 carbons, like dodecane, that would be a very, very high boiling point compound, and this is how refining works. So if you work in the petroleum industry, who knows how long that's going to stick around. Still, it's still a big thing. The earth burps up all this, well, it doesn't, it used to burp up all this black stuff Now we got to go looking for it. You know, in the 1800s in Pennsylvania, it just came to the surface, and they're like, hey, look, the Earth's burping up stuff. I'm paraphrasing there a little bit. I'm not really sure that that's what was said, but they found out that that was flammable, and that's our fossil fuels, right? Well, you know, you can take all this black stuff that the Earth burps up, you can flare off all the gases or capture them if you want to make natural gas, and then you can separate by boiling point through distillation all these liquids, and then the heavy stuff you go make garbage bags out of, and then the little bit lighter stuff you go and make you know, motor oil, and then a little bit lighter than that you make jet fuel and diesel, and then even around C8 octane you make gasoline. But here's the thing, folks, let's not talk about fossil fuels anymore. Let's talk about something nice and pleasing, like wax. If you're going to have a candle, paraffin wax, that's a solid. So even if you make this thing outrageously big, it's going to eventually solidify, and that's nothing but nonpolar. But still, it's got stronger intermolecular forces than water. So actually there's an overlap, folks. There's an overlap where actually the dispersion forces can become so strong that they're actually greater than hydrogen bonding. And you notice when I was trying to take examples of hydrogen bonding last video, I tried to compare things with equal grams per mole. So if you wanted to say, hey, what's the intermolecular forces in this compound going to be? This is H2O, 18 grams per mole. Well, I should really only compare things of like grams per mole, because polarizability is really dependent on grams per mole. Basically, it's just, you know, the bigger the cloud is, the larger the molecule. All right, and then I'm going to leave you with one more thing. I'm going to ask us to go a little further with a conceptual vision of this. So what happens is, if you have even two things of the same formula, like let's make butane. There's butane. And I should have taken a shortcut, because you can, so you got two butanes coming up next to each other. And sorry this is taking me so long to draw, but that was an H right there that I squiggled, but you're going to have to just deal with it, okay? And so there you go. This would have a greater strength in London forces than if I put a branch in it. Same formula, but do you see how there's like kind of like less surface area? If two of these came up next to each other, that kink, that branch that we put in there is going to not allow the others. I'm too lazy to draw another one, guys. And I want to make this video shorter, and I just banged the camera, and so it means it's time. Karma is catching up with me for all the dumb jokes. But you see where that branched alkane, that branched compound would have less surface area if another neighboring one like it came up. But if you have straight ones, those would have greater proximity with each other. So, in conclusion, London forces are a combination of collisions, because not everything is at absolute zero, everything's in motion, proximity, and then the bigger the molecule is, the stronger the London forces. So, folks, you have graduated from IMF boot camp. We talked about ionic forces, we talked about ions with dipoles, we talked about dipoles with dipoles, specifically hydrogen bonding, and now we've explained every kind of compound, how these things can have attractions for each other, and how they can become a liquid or even a solid. Guess what's coming next? Liquids and solids. And then we're going to apply the, notice we haven't done any math yet. That'll come to an end soon. But we are doing just theory, and then you should be able to sort of rank things according to what their boiling point would be. Now, don't get me wrong here, folks. I'm not into making all sorts of conflicting variables, all right? So if I said, hey, what's got a greater boiling point? You know, propane or something about the same mass as it that's polar, you'd say, well, it's probably the thing is same mass of it that's polar. But, you know, I wouldn't ask you to say what's got stronger intermolecular forces, something like C2H46, which is gigantic and actually a solid, and I'm not expecting you to remember that, and something that is a little bit less gigantic and polar. You know, it turns out that the London forces can supersede the strength of things that are polar. Think about it. Water's got really strong hydrogen bonding, but it ain't a solid at room temperature, but paraffin wax is. So, you know, basically, but then you could take ionic, you know, NaCl. Well, you know, you could use your imagination there. You know that's a solid, and you know it's got a boiling point of like hundreds of degrees Celsius. But this little pecking order of intermolecular forces determines at a certain temperature what phase something is in, or what temperature is required to make it turn into a liquid if it's a solid, or a gas if it's a liquid, and that kind of stuff. So it's really going to be the foundation for you as we discuss boiling points and things like that next. By the way, I've talked about boiling point, but we never really said what a boiling point is. That's coming next. Hope you're doing well. We are deep into it, folks, and we might even do some math in a couple more videos, something like that. All right, folks, have a good day. Be nice to each other. Bye.